Simon White, I think that I actually don't really need to introduce him, so because I think everybody knows him. But let's anyway give a short introduction to Simon. He did his PhD in 1977 in Cambridge with Donald Bell, and then he moved to an impressive number of places. I highlighted them here: Berkeley, Virginia, Cambridge, Paris, Princeton, Arizona, Jerusalem, Garching, Durham, Munich, Shanghai, Beijing. So he's been basically everywhere. And of course, he has also had an influence in a very big part of astronomy, in galaxy formation and in cosmology. He has, of course, he has also had a number of prizes and honors. For instance, I'll name a couple. The Fellow of the Royal Society, 1997. Gold Medal of the Royal Astronomical Society 2005, Max Born Prize 2010, the Global Cosmology Prize 2011, and I found it very interesting, the honorary citizenship of the city of Padua. As a scientist, you can become honorary citizens. So Simon has, of course, put a stamp on a lot of parts of extragalactic astronomy. We all know it from the White model, galaxy formation, and his influence on the Loveless EDM cosmological model. And with Volker Springel, who we managed to get to Heidelberg here, he made, of course, together with him, the Millennium simulation, which is, of course, a very important influence in cosmology. Well, let me now stop because I think we all are very interested to hear what Simon's going to tell us. And so please let us give him a warm welcome.
So thank you very much, Kees. It's great to be back here in Heidelberg. So what I'd like to talk about today is formation and evolution of the galaxy population as a whole. And in particular, I want to concentrate on our simulation technique, which doesn't aim to understand the detailed structure of individual galaxies, but rather the systematics of the galaxy population as a whole and the way it's evolved with time. So let's start with some background. So this is the Planck map of the microwave background. So this is the boundary of the visible universe. We don't get any light directly from anything behind this because this is the scattering surface. So that's as far as you can see. And what we see here are these fluctuations, which are a few parts in 100,000, the initial conditions from which all present structure is formed. And because we can measure this quite precisely, and because the fluctuations are linear, and so we can use linear theory to describe them, we can characterize them, as it turns out, almost completely by their power spectrum. So this is a famous plot of the power per mode as a function of multipole or as a function of angular scale in the sky. This is very large scales. This peak is at 1 degree, corresponds to the universe being flat, and this is the small scales. And this is the results from 2013. They got even more precise in 2015, but you can't tell the difference when you look at the plot because the other bars are already tiny. And the curve here is a theoretical curve from our standard model, and it's a very good fit. And it's a very good fit because you've adjusted 6 parameters, as it turns out. They all have physical significance of one kind or another. These are the values. It's striking what the level of precision is. So this is the number of baryons in the universe, well, mostly protons and alpha particles. We know this to 1%. Even more interesting, this is the amount of non-baryonic matter in the universe at a redshift of 1000, long before the structure formed. This is a 40 sigma detection of dark matter. And using no information for the present universe at all, only using what we see on the last gathering surface. And if you go to the most recent paper, there's now 860. So we've measured the density of non-baryonic matter in the universe when it was only 400,000 years old to a precision of 1% in grams per cc. This is the mass in grams per cc. So we don't need galaxy rotation curves or gravitation or anything else to see dark matter. We already have a 1% measurement using just linear theory and nothing in the present day universe. However, these scales, which we see in the last gathering surface, are relatively large. And so, for example, for a small-scale structure, typically we talk about characteristic fluctuations, which today have a scale of around 8 megaparsecs. For historical reasons, this is a characteristic scale which is often used, where the present non-matter distribution is roughly non-linear on the scale. That's here, approximately on this plot. So what you see is almost all the measurements are actually on scales which are larger than the non-linearities in the present universe. And so this means that because it has constraints on only very large scales, they tell us only certain things about dark matter, but not everything we would like to know. And in particular, they can't tell the difference between cold dark matter, where thermal motions were irrelevant early times, and warm dark matter, where perhaps fluctuations were significant, where velocities were significant in early times. So then we can ask, is there any other information about the structure which can test this standard model on smaller scales? And it turns out the best information comes from looking at the absorption along the line of sight to distant quasars. And this is absorption by the intergalactic gas between us and quasars. So this is not an observed spectrum, in fact. This is a simulation of the absorption spectrum of a quasar relative. So unabsorbed would have flux 1. The actual flux is here. You can see it's absorbed by the neutral hydrogen along the line of sight between us and the quasar, which is a small fraction of the total intergalactic mass, most of it's ionized. But nevertheless, there's enough neutral hydrogen to cause this absorption. And the structure in the absorption reflects the structure in the gas between the galaxies, which has not yet collapsed to make anything. And what you can see here is that there are 3 different curves. This is the prediction if you have cold dark matter, and this is warm dark matter for 2 different assumptions about the mass of the dark matter particle. And what you can see is as the mass goes down, the particle gets warmer, that it has more thermal motion than early times, and the structure is gradually washed out on small scales. So the structure you see here is actually sensitive to what the dark matter is like, and what structure is like on scales much smaller than are visible in the microwave background. And what happens is high frequency power is missing in the warm dark matter case. So this is currently the best limit, so these are measures of power spectrums, and this is spatial wave number. So the scales of the microwave background corresponds to over here somewhere. And these are all smaller scales, so this is smaller scale going to the right. These are the smallest scales. And these are a power spectrum measured from the absorption spectrum of galaxies. These are different redshifts, so 2.2 here, 4.2 here, these are all from the slow digital sky survey. And then these higher redshift measurements come from bigger telescopes. And what you can see is that the measurements are the symbols, and the colored curves are the predictions of a model which has the same structure seen in the microwave background, differing only in one is warm dark matter, the red dashed curve, and one is cold dark matter, the green curve. And what you can see is that the highest redshift in the smaller scales, there's already a substantial difference, and the red curve is disfavored. So if you interpret this as a limit, this puts a lower limit on the mass of the warm dark matter particle, which for the particular model is being used here is about 3 keV. What do the differences look like? Let me show you a simulation. This is supposed to be the dark matter associated with something like the Milky Way, the dark matter halo. This is in a cold dark matter universe, and this is in a warm dark matter universe. These have nice movies, so you can see, just rotate them around. What you can see is the central density is about the same, the mean structure is about the same, and we can see there are many, many small lumps of dark matter in this case, which are not present here. And this is just because of the suppression of the small scale structure, you don't make any small lumps in the warm dark matter universe as you do in the cold dark matter universe. If you look at the evolution, this is the cold dark matter universe, this is the warm dark matter universe, this is time coming forward. You You see, you start to make structure in the cold dark matter universe long before you do in the warm dark matter universe. It's only just starting now. So the early phases look very different in the two cases. This is still high redshift. It's 1 billion years ago. You see now, as the structure gets stronger, you can see they start to look more similar. So what happens in the warm dark matter universe is this less small-scale structure, and the structure forms later. And the assumption here corresponds to a mass for the dark matter particles, which is already ruled out by the Landau forest data that I showed you earlier. Okay, so this has had the smoothing effect is too strong to be consistent with Landau forest in this simulation. So the effects for something which should still be allowed will be weaker. So what you can see is that the Milky Way's halo itself looks the same, and actually most of the more massive things also look pretty similar by the present day. The differences are high redshift may be more important. So what this means is that we have direct observational evidence that the cold dark matter model is a good description of the initial conditions for structure formation, and essentially all scales relevant to galaxies, except possibly the very smallest ones. Okay, so we know the initial conditions. How well can we predict what happens? So if you take these initial conditions, put them into a computer, and just integrate forwards, if you ignore all the complicated stuff, all the barriers and the stuff you can actually see, you just integrate the universe into cold dark matter, you can predict what comes out with pretty high accuracy. And now this has been going for long enough that everybody pretty much agrees on the outcome. And you can predict the number of objects. This is abundance as a function of their mass over quite a wide range of scales. You can see this is 8 orders of magnitude in mass and 12 orders of magnitude in abundance. And the uncertainties are roughly given by these different simulation resolution, roughly the 10% level, or less if you try to be precise. So we can predict what happens with dark matter from these initial conditions to very high accuracy. And what you find is that if you get a lump, and this is supposed to be a simulation of a halo, the reproduction is not very good here, it has many small lumps inside it. If you ask, where are the galaxies? This would be a galaxy cluster, might be one galaxy in the middle, there'll be also galaxies sitting in all these other halos here. So what corresponds to the galaxies in such a simulation is not the halo as a whole, but each of these separate units. You might expect to have one galaxy in each of them, and the question is how big should that galaxy be? What should it look like? Is it consistent with what we see? So the galaxies correspond to self-balanced sub-halos inside the halos, not to the halos themselves. So a cluster halo like this might have hundreds or even thousands of galaxies in it. So the information relevant to galaxy formation inside such a simulation is encoded in the properties of the subhalos and how, with time, they gradually merge together to make bigger and bigger objects. So if you take a single object with a single center at the end, some subhalo, if you go back in time, might be in different pieces. Each of these at early times would have a different galaxy in it, but the galaxies may all merge by the time you get to the end. But if you take an object which still has many pieces, then it would have many galaxies in it. So this is time this way. This is how the mass can aggregate. So people talk about trees. You can imagine a tree structure superimposed, which is the way you represent the growth of the final objects. So how do the galaxies themselves form? Well, the gravitation is dominated by the dark matter. So initially, that does most of the pulling. But once you get a nonlinear object, the gas can then cool off and sink to the center. So there's a process which you can think of as condensation. As you cool, you become more concentrated. So you can think of the galaxies condensing the center of the dark matter potentials, which of course are evolving with time. So this picture has been around a long time, 40 years now. So in this kind of picture, the halo gravity controls the assembly through the accretion and merging of all these lumps, but it's effectively the radiative cooling which controls the gas supply into the central object, because that determines how much gas can get to the center, get dense enough and actually start turning into stars. So even at this level, you can find two different kinds of behavior, which is recognized, actually was even recognized before this by a recent Australia in 1997. A paper that Carlos Frank and I wrote in 1991, we went through this in some detail, because if you have an object which collapses and it's got hot gas sitting inside, you can ask, how quickly can that cool? So typically an object will be dense in the center, and the density will get weaker as you go outwards. So this means because the cooling time scales strongly with density, the cooling time will be short at the center, will radiate its energy quickly, and will get longer as you go outwards. So you can identify some particular scale inside any object where the cooling time is equal to the age of the system. So if that scale is very small, then basically the system will just sit there because it can't radiate away its energy. If that scale is very large, it will radiate very quickly, and the gas will lose pressure and fall to the center. So you can define a radius, which is the radius where these two times are equal. The age of the system is equal to the rate at which gas can cool. And when cooling is large, essentially the rate, when the cooling radius is large, that means cooling is very efficient. The rate at which stuff can fall into the galaxy is just the rate at which the object itself grows. You can make a simple model for this. And this is rapid infall, is saying all the barrier material which falls onto an object in principle can turn into stars because the pressure can't hold it up and it will fall to the center. In the opposite limit, where the cooling radius is small, then the rate at which stuff goes on the center is just limited by how rapidly it can cool off. So then you can write the rate at which the center is the rate at which this cooling radius is moving outwards as time goes. So the reason I'm showing you this is to show you can then make simple, essentially analytic models which encapsulate the physical behavior. And you see immediately there are already two regimes which people rediscovered eventually when they could run simulations which were able to follow this process in enough detail, and then rebaptized it and made lots of noise. So if you can make plots like this, which show you that already this is interesting, or it gives you interesting results. So what's being shown here, this is the accretion rate, and this is, if you take an object, this is an object with a characteristic velocity, say the Milky Way would have a characteristic velocity of 200 kilometers a second would be here, smaller galaxy 100 kilometers a second would be here, 30 kilometers a second characteristic velocity would be here. And what you can show then in this plot is this line, which is the rate at which gas is becoming cosmologically, the infall formula I showed you, and these lines which are where the gas is going to come in if it comes in by cooling, so if cooling is dominant. And so what you see is, for example, for the Milky Way, here, these curves are assuming no heavy elements, and you can see that the cooling rate due to radiant cooling is much less than the infall. So lots of stuff falls in, but only a small fraction of it can cool. Over here, small objects, basically the cooling rate is very high, higher than the infall rate, so basically everything which can fall in will cool. So the result you see immediately from this is that in small objects, corresponding to dwarf galaxies, you can cool off rapidly at any redshift, so cooling does not stop the formation of small objects. If an object collapses in a cold dark matter universe, it will be able to cool at any redshift. So this is redshift 0, 1, 3, 7, and 15. On the other hand, you take something in the Milky Way, which is about here, then heavy elements are important, so that's why I put it on this side. You can see today, at a high redshift, it's still true that the cooling curve is above, so at high redshift, even things with the mass of the Milky Way will be able to cool all the gas which falls in on them. But at low redshift, actually the cooling curve is below the infall curve, and so you expect them to build up a halo of gas which could not cool. So this was already clear, how long ago that is, more than 20 years ago, there were different regimes. So now let's go and look at the observations and find out what we can say. So an interesting question is, you could ask is, where does a typical star live in the universe? So this is what happens if you take a representative region of the universe, and for every star in that region, you count one in a bin which corresponds to the stellar mass of its galaxy. So our Milky Way has a stellar mass of a bit more than just under 10 to the 11 solar masses. So all the stars in our Milky Way you put in the bin here. Stars in a dwarf galaxy of 10 to the 8 solar masses you put in the bin here. Stars in a very massive galaxy approaching 10 to 12 solar masses you put over here. If you make this histogram for all the stars in the universe, you get this curve. Because I plotted 12 orders of magnitude on this scale, you can see this looks really narrow. So there is a very well-defined characteristic mass of galaxies, and it turns out to be pretty close to the mass of the Milky Way. So we're living in a very typical galaxy from that point of view. our suns in a typical galaxy. Now, the reason for showing this is you can do the same thing in a standard model for the dark matter particles. So you ask, take a random dark matter particle, what mass object is it doing? Then you get a curve of things like this. You see, this shape is quite different. In fact, it's not zero here. 25% of the total mass is to the left at this point. So this is not at all localized. So there's a very large difference. Galaxies like to be at this very well-defined scale. The dark matter has a much broader range of scales. So we need to understand physically where that comes from. So what this means is if you take, say, the Milky Way, and you know how many baryons it has in it, we can estimate what we think the dark matter mass is in its halo. We can take the ratio, and we get about 3 to 4%. If you take a very massive galaxy, a rich cluster, say, take the M87 in the middle of the Virgo cluster, and take its mass relative to the mass of the Virgo cluster, you get a much smaller number. And if you take dwarf galaxies, you don't know very well what the halo masses are, but you estimate what their mass are, you also get a smaller number. So you get a curve which is a very characteristic shape, just from combining the two curves I've shown before. It shows you the fraction of the mass of the halo which is sitting in the stars in the central galaxy. You see that maximizes about here, which is about the halo mass of the Milky Way, at a few percent. So the first important thing to realize is this is still less than a quarter of all the baryons that we think ought to be associated with the Milky Way's halo. So one issue is where are all the rest? So the stars, even at the most efficient point here, the galaxy have only managed to turn roughly 25% of the baryons we think should be associated with the dark matter in the stars. The Milky Way, at least, we don't still know where the rest are. So we're missing 75% of the ones associated with the Milky Way. If you go to smaller galaxies, the situation gets worse very quickly. You rapidly get down a few percent of the baryons are in the central galaxy. We don't know where the rest are. If you go to very big halos, the efficiency in the central galaxy goes down, but at least we know where the other baryons are, because those we can see. Most of them are actually in the intergalactic gas between the galaxies. We can see it through the X-rays. So the usual argument is that what's happened here, it's an argument which goes back to the last in 1974, is that in small galaxies, you form a couple of stars, and as soon as the first stars go supernova, they blow the rest of the gas away. So then it stops. So supernova feedback is supposed to be responsible for this end. That doesn't work over here because potential wells are too strong. And over here, the usual argument is this is partly due to the fact that the cooling efficiency is lower, but that's not enough. You need something else as well. The usual argument is this is somehow to do with black holes and feedback from AGN. And there are various models showing that this can work, at least in principle. So that means if you try to just keep track of where the baryons are, if you take a particular halo, so what we have, so there's the galaxy halo to mass ratio very strongly with the mass. You can take all the baryons associated with a particular amount of halo and say, well, where are they? So the total amount we expect is the cosmic baryon fraction times the mass of the halo. So a halo of this mass, that's how many baryons you think you should have. So where are they? So some of them could be in stars, some of them might have made a black hole. Some of them could be in the interstellar medium. Some of them may be in hot gas, like the hot gas in clusters. And some may be thrown out. So there's at least 6 here. Maybe obviously you may find the splittings. Now the problem is this is already really complicated because we already know from looking at galaxies many processes which control the movement of material between these different reservoirs. So the infall from the intergalactic medium may make hot gas, or it may cool off immediately to make cold interstellar gas at the center. Once it gets dense in the center, then it may make stars through star formation. Star formation puts some material back into the interstellar gas. It may reheat some of this gas back up into a hot halo. It may blow it out directly. But then some of this may turn into a black hole. Then the black hole may also influence the cooling, or may even blow material out. When the material goes out, then you'll have galactic rings, and some of this may fall back. So there are all these processes, all of which can be seen in action in different places. So we know they're all important in some galaxies. What we don't understand is what controls the different processes. So I showed you a couple of simple formulae which give the infall here and the cooling here. So now, if we want to control this system, or to understand its evolution, we need to put in all the rest. So you can put in equally simple formulae for the other things. So for example, if you have a certain amount of gas in the interstellar medium, you can estimate how rapidly it makes stars. And there's a formula which is usually called the Kennicott law. It's not a law, it's just it's a phenomenological observation. There's something, a very simple formula, kind of like this, with an adjustable efficiency here, fits in galaxies. Here's a model for how, as you increase the mass of the black hole, you can get energy out. That depends somewhere on the mass of the black hole, on the material you're accreting, some efficiency you don't know. We don't know how these are phenomenological formulae, so you can make plausible guesses of what they should look like. We don't have a priori models which allow you to say exactly how they work. So then we have all these processes. We need to try and track this in a single object, and so over the population, you need to put in similar modeling of all of these things. And if you look at this, you ask, say you try and do a more detailed simulation, which parts of this can you get rid of? Maybe you can deal with the cooling. You can't deal with the star formation, usually that's always put in by hand with a formula like this. You can't do the accretion onto the black hole. This is put back in with a formula somewhat like this. So only certain aspects of this could you get rid of by actually trying to do a more detailed simulation than the ones I'm showing you. So what I'm going to show you is what happens if you try and model all these processes with simplified analytic formulae of this kind. So this is what's usually called the simulated program. So the idea is you follow the dark matter distribution with the high resolution simulations. What this allows you to do is to find all the dark matter halos and their substructure and to follow how this evolves with time. So you have the context defined by the dark matter. So this describes the growth, internal structure, and spatial distribution of the dark matter. Now we have to deal with the baryonic physics for all these processes that I just showed you. And the idea is to use simplified models for these processes, which will have unknown parameters, the efficiency of star formation, efficiency for heating, scaling parameters like how the heating varies with the density of the gas, or with the mass of the black hole, or the temperature of the surrounding gas. So there are many parameters, even in simple descriptions of this. And then the question is, with physically plausible descriptions, not necessarily correct, but these physically consistent descriptions of these processes, can we understand how the present properties of the galaxy population evolve from what we see at high redshift? And so we want to take the observational data on the galaxy population and infer the efficiencies and scaling parameters of these processes. This is similar in a way to taking the microwave background pattern and inferring the cosmological parameters. You have a well-defined observation, in this case the temperature on the sky, and you have in this case only 6 parameters in your model. Some people say 6 is a lot, but anyway, 6 parameters in your model that you want to infer from it. So, microwave background works really well, everybody's very happy. We have 6 parameters, very small error bars. The question is now, how many parameters do we need to fit the galaxy population? Because the galaxy population, and this is not a small number of objects now, they're roughly, the Sloan survey has spectra for 1 million galaxies. Now, for every galaxy, you know not only its position in space, its velocity, but you know its brightness, you know its size, you know its metal content, you know all sorts of things, its star formation rate. And obviously, we have known many things. So we have an abundance by mass, size, gas content, star formation rate, large to this ratio, AGN content, scaling relations between these things, the detailed spatial distribution. So how many parameters is this? I mean, even the dimensionality of the space is high. So we have maybe 1 million objects in a 20-dimensional space. So with 1 million objects, you have high statistical precision in principle, but we don't even understand the parameter space. So I think, how do you start to go to this problem? So I think, these are complicated objects. I think you can take a lesson from the microwave background, is if you are going to fit parameters and you want them to be useful, then the parameters should have some physical meaning. If you fit a purely statistical model, you can probably make it fit, but then what do you learn from the values of the parameters? For the microwave background, we had 6 parameters, but they were the density of baryons, the density of cold dark matter, the curvature of the universe. We care about those things. So if the parameters we're using here also represent aspects of the physics you care about, then you can say you've learned something when you constrain the values by fitting the data. So this gives you a tool to understand how these different processes interact with each other and the effect the stars and the gas as objects grow. And then we want to understand how these processes are reflected in the population properties, their abundances, their scaling relations, their clustering, and how these evolve over time. And then you can then interpret large surveys in terms of the rates and efficiencies of these processes. We're still not pretending to make an a priori model for the physical evolution. We cannot treat all the physics. This is also true for more detailed hydrodynamic simulations. You cannot treat all the physics. You cannot make an a priori model. You can treat more of the physics in a quantitative way, but you still have to leave out critical aspects. So the Millennium simulation is the first large simulation of this kind. Volker made a beautiful picture, which was why I got onto the front copy of Nature. I think what was interesting, though, was that they, apart from surprising dinosaurs, they focused on the fact this was a simulation of 20 million galaxies. So they got that right, actually. The thing which was new here was not so much the dark matter simulation, even though that's what made the nice picture, was the fact that it actually was able to simulate the evolution of a very large number of galaxies. And because, of course, you can not only compare them, here's the simulation, with direct observations of the clustering, relatively low redshift, but you can also look back in time. So you can make a light cone which goes here from redshift 0, back in time here to redshift 3. This is what you would find if you, because you have, in order to make the simulation work, you have to get the evolution through cosmic time, so you can predict what you should see along the past light cone. And so you can compare with evolution of the population of galaxies. So this went public, finished in 2005, went public in 2006. And one of the things that we did was to make a public database through the German Astrophysical Virtual Observatory, so the theoretical part of the effort, and made this interface public. And it got a lot of use. Up to now, there are 700 publications that have used data, actually used the simulation data from this. And it's quite interesting, this is now an old simulation. It was completed in 2004, I think, published in 2005. You can see that actually the rate is still around 75 a year, and it's not tapering down, even though there's been plenty of time for people to do more. And if you look at these, almost all these publications use the galaxy data, and they're by people who are unassociated with the people who carried out the simulation. Most of them, of course, just use it to say, I compared this with the standard model and look, it doesn't work. Mostly people want to prove the standard model is wrong. So, some of them say it's work, but I'd say there is probably at least 60 to 70% find something that doesn't work. But that's okay. So I think the reason this has been so heavily used is A, it is publicly available. It was, until recently, it was not common to make simulations publicly available. It's relatively easy to use. I mean, you have to learn a query language, SQL, but it's quite simple and it's really quite powerful. It allows you to do a lot of things. And it provides data in a form which are easy to compare with observations. In other words, you can find a light cone and you can get things as a function of magnitude and redshift and angular size. So it provides the data in a form which are relatively easy to compare with the observations. And I think also the results are for models which are simple but still physically based. So I think these are the reasons why it got so much use. On the other hand, it was quite limited. The most obvious limitation is there's almost no information about the internal structure of the galaxies because the resolution, we're just not looking at that. In addition, the resolution of the simulation, because we wanted to look at big volume, means you can't see the dark matter structures that correspond to small galaxies. So in the original simulation, it was, the resolution was too poor to model dwarf galaxies. And there are lots of people who are interested in dwarf galaxies, even though they contain a negligible fraction of the stars in the universe, as I showed you earlier. Also, because it was just one simulation, you couldn't tell whether the results were a physical consequence of the model or just limited by the resolution of the simulation. And you can't do a convergence test. The volume turned out to be too small for people who want to do precision cosmology. They want to look at a large fraction of the universe, and then the simulation was too small. Of course, by today, because we used what was popular in 2003. That's not popular any longer because cosmological parameters have changed. So the simplest way to deal with the resolution issue is just to repeat the simulation with higher resolution. So we did that already in 2008. Same number of particles. We took a volume that's a fifth the linear size, which means that the individual dark matter particles are 125 times less massive. So we just changed the mass resolution and spatial resolution by giving up on the size of the volume. And then we did everything the same way. So the results here allow you to do resolution tests on the original results, see if they were some sensitive resolution. And then when you understand that, to try and go to smaller scales. So then the next generation of models implemented modeling simultaneously on the two simulations, tested the convergence, and then extended to dwarf galaxies, and proved things that we already knew were wrong with the physics. So let me show you reasonably how all this works. So this is the number of galaxies as a function of their mass in stars. And observational data from the Sloan survey, which we're using to calibrate this, are shown by the symbols. And then the results for the model tuned on the two simulations together is shown here. So this looks really good, but that doesn't mean anything. It's because we use these data to settle the parameters. And there were a lot of them, 20 at least. So, okay, what this shows that it is possible in this context to fit the data. But, there's more than one way to fit the data with 20 parameters. What you can see is if you run the same model on the two simulations, they actually agree extremely well over all high mass scales, above here. So you can test where the convergence starts to break down. You can see as you go to low masses, you lose objects in the later simulations because you can't see them. So now we actually have a convergence test. Now we know how well things can converge. You can actually look at other things. So for example, you can see, well now, does this model work for fainter galaxies? Well, this is the number of dwarf galaxies around the Milky Way, and these predictions with different assumptions about ionization history. You can see the simulation predictions of black. They kind of work, particularly the one in the middle. Turns out this is now thought to be the best model for reionization, so it doesn't, it's over-predicting a bit, but roughly the right number of small galaxies. So now you can at least test outside the range which you use to set your parameters. And then there are lots of other things you can look at, like the scaling parameters, how galaxies properly scale with their size scales with their mass, the mobilicity scales with their mass, their size, how the characteristic velocity scales with their magnitude. So you can try and test against these kinds of data. And some things fit reasonably well. You can see some things fit, some things don't. Here, for example, the scatter in the observations is much less than the scatter in the models. It doesn't work very well. Here's an interesting one. Let's look at the spatial distribution, because the clustering was not used as a constraint. So the points here are the clustering of galaxies in the slow visual sky. So the highest mass galaxies here, lower mass, lower mass, lower mass. And these are the clustering measurements, so the autocorrelation function. You can see the error bars on the measurements are really quite small. And then simulations are shown by the continuous curves. And there's a blue curve and a black curve. And the blue curve and the black curve are two simulations differing by a factor of 100 in resolution. So what you can see is the blue and the black curve agree with each other perfectly in all patterns. So you strongly the clustering is converged. The result is a result of the model. It's not to do with the numerical resolution. And what you can see is the model fits the data for high mass galaxies, and it fails to fit the data significantly for low mass galaxies. So this is what you expect. These data were not used to constrain the model. It would be amazing if it turned out to fit. And of course it doesn't. That means the model has to be refined. So we learn from this that there's something wrong in this model. And whatever it is causing small galaxies to be too clustered on small scales. So maybe they should have been disrupted or torn apart or something else. Other things don't work. The data were only adjusted using the present-day population of galaxies. If we look at the galaxies in the past, this is the number of galaxies as a function of their stellar mass. This is at low redshift, higher redshift. This is redshift 1.3. This is redshift 2. And the theory model prediction is the green curve. So it works at low redshift because we set it up that way. if you've got a high redshift, it doesn't work. Why is that? Well, what's happening is that you've got a high redshift, the green curve is staying more or less in the same place. That's because the small galaxies actually form a quite high redshift in this model. In the observations, they've gone away. See, it's down here by almost a factor of 10. So the small galaxies in the real universe clearly formed later than galaxies in the model. So again, we've learned something. Something about the way the galaxy formation is treated is making the efficiency of star formation much too high redshift in the low mass objects. And skip this, I'm out of time, as usual. This is interesting. One of the things that we looked at was how to switch here, between cosmologies. The question is, I've been concentrating galaxy formation physics. Does it matter what the cosmological parameters are? So if you change the cosmological parameters, does it make a difference? So as I said, the simulation was originally one with W-map parameters, which had a density of the universe of a quarter, and now this is the amplitude of fluctuations in the present day, which is now thought to be relatively large. So now let's say, well, maybe nowadays we think the density of the universe ought to be higher, the amplitude of fluctuations ought to be lower. I put in the 2013 Planck values here. Does this make a difference? Well, it turns out for the dark matter, it does make a difference, but you can take most of it out by just scaling the simulation. And if you scale the simulation's size, the number of megaparsecs you assign to your box, in an appropriate way, you can actually match the initial conditions for the new cosmology quite well, because it's not really that different. So you don't have to scale very much. And then you can get the amplitude right by just reinterpreting what the time is, which time in the simulation you can simply be the present day. So with these two kinds of scaling, you can actually get most of the evolution in the dark matter distribution to agree quite accurately with the 40% level. And so, for example, if we get from W-map to Planck, you have to change the size of the simulation from this original size to this. And the redshifts, which correspond to 0, 1, and 2 in the Planck cosmology, were these redshifts in the original cosmology, it's the amplitude smaller. And then the particle masses and velocities have to be scaled in the same way. So you do this, then it turns out, at least for the dark matter level, you can get a close match, so then we can see what does this predict for the galaxies. And it turns out, well, things do shift, but we have all these parameters we set to fit, for example, the mass function. And in the end, if there's enough flexibility, you can get just the same answer. So, it didn't really make any difference. Changing the cosmology did shift things, but by shifting the galaxy parameters, which we don't know, we're trying to estimate them from the data, we can get back to where we were before. So, just changing the abundances didn't really help. Did help a bit with the clustering. So the red curves here, the ones I showed you before, you can see they're much higher than the observations. Now in the new cosmology, it's got a bit better. Still not there, but at least it's closer. But the problem we had here with the abundances of galaxies, this is the difference between the two cosmologies, made no difference at all, basically. So it didn't help. So whatever was going wrong is something to do with the galaxy formation, it's not something to do with the cosmology. Okay, so how do we define this? So we have this is just a digression on the model. So we have a model which, there are lots and lots of parameters because every formula you put in has scaling relations which you've had to guess. So if you took them all, you'd have 30 or 40 parameters in your model. Many of them we can make at least a rough guess what they should be. So if you take the parameters which significantly affect the outcome, there's still 15 or 20. So you have a 20 parameter space. How can you tell whether you've got a unique answer at all? So one way to do this is just to explore the parameter spaces using multicolored Markov chains, which basically just throw dice and move around the parameter space at random, finding things which are reasonable fit to some set of data that try to reproduce. So one thing you can do is try with the model that we had in 2011, which was fitting the low redshift data, which failed at high redshift. You can say if we just take this model and we try to fit its parameters, to fit the data at each redshift independently, can we get a fit? And the answer was, well, yes, 20 parameters, you can get a fit at every redshift. And now you can ask, is there one set of parameters that will actually fit all the redshifts? The answer turns out to be no. And that you can see here. So these are the regions. It doesn't really matter what these parameters are, but these are just, this is one parameter of the model. This is the second parameter. The same parameter here, but a different parameter there, so on. And so there are actually 7 parameters in this plot. And you explore the chains, and these are parameters that give a good fit to the higher redshift mass of abundance of galaxies. Here, intermediate redshift. Here, low redshift. What you can see is that these parameters are not consistent with each other. Actually, they're 1, 2, this is the 4. I got mixed up. This is the same pair of parameters. This is 4 different redshifts. This is a different pair of parameters, 4 different redshifts. Yet another pair of parameters, 4 different redshifts. So what you see if you look at this one, well, you can find a set of parameters that's more or less inside the contours of all redshifts. And of course, you always get the smallest contours at the low redshift because that's where you have the best data. So it's the most constrained. This one, well, more or less, you can get things. This one, there's no way you can get a value for this parameter which fits over the high and low redshift data. So this is a way you can explore your parameter space and figure out what you have to fix. So, you know, these are working more or less, but clearly, the thing controlled by this particular parameter is not working. And what this parameter is controlling, it turns out, is when the winds blow material out of a galaxy, how long does it take for that material to fall back? Does it fall back, and how quickly? And that's what this particular parameter is controlling, and clearly our initial assumption didn't work. So that's what we learned. We learned that it had to scale differently. So initially, the scaling that we assumed was that the time to fall back in went with this particular scaling. Now, if you change it to this particular scaling, suddenly everything will fit. It's the same number of parameters formally, but it's a different assumption about the scaling. So this, and then these are the abundances of the different redshifts, and now you can see the old curves, the dotted lines, you can see it off substantially. And now you can find parameters that do fit. Okay, so now you can not only learn that our initial model was wrong, in fact what was wrong and what you needed to fix. And then you can see if it fits other things. For example, this is the abundance of galaxies. These are the ones that are not making stars, and these are the abundance of galaxies that are making stars, which is 0, 4, 1, 2, and 3. And what you can see is, with the new, you're kind of getting a fit reasonably well to both of these as well. So now you're getting roughly the right abundance of galaxies at all redshifts, and roughly the right fraction of them making stars. You can look at other things like this is the star formation rates. So if you ask what did we update, every time you update the model, so we fix these things, and of course there are other things which were wrong, or bugs. Codes always have bugs, so that some of these show up. So you keep fixing things. You ask what was efficient. We had to adjust the efficiencies of some of the processes and the way they scale with redshift. We had to reduce the environmental effects on small galaxies around big ones because they were too strong in our original model. We had to allow more star formation in small objects, and we switched to the kind of popular cosmology that fits better. I'm skipping details because I don't think it's, I can show you more detailed things that fit. It doesn't really matter. What I'd like to show is one other thing that is a kind of an experiment along the lines of improving the virtual observatory aspect. So this is something which I'm not convinced about myself, but some of my collaborators were very convinced of, and this is what observers really want, is to give them your model just like they got it from the telescope. In other words, a CCD image with cosmic rays in it and everything else, and the missing columns. So this is really what they want. I'm not sure this is really what they want, but anyway, this was what we made for them. So we have a thing called the Millennium Observatory. The idea is to construct deep light cones, so because the models actually have all the information which is needed to do this. So you construct deep light cones out to redshift 10 or wherever you like in arbitrary directions, and you can do this now inside the observatory to include, say, a cluster of redshift 0.7. Because in simulation you can find a cluster and then you can point the telescope in that direction, at any desired redshift, and you can pick the cosmology you want too, because we know how to scale now the models in different cosmologies. And then once you've done that, what the machinery will do is project each galaxy into the sky using the size, mass, stellar population, and orientation that we have as inputs to standard profiles for this to make an image. You choose a population synthesis code to turn the ages and masses of stars into colors and put in dust and things. And then you redshift it. You include the intergalactic absorption on the line of sight to make observer frame photometry. And then you even you emulate the Hubble Space Telescope or Gemini North or the VLT or whatever you want to get a reasonable, get a pixel scale, point spread function, counting noise, which corresponds to real observation. And then you can make an observation, and some of this is already accessed. So then you can take, this is a real cluster. You can tell it has gravitational lens arc in it here. And you can take a cluster at the same redshift, simulation, make an image, it looks like this. The theorists might think this looks good. The observers will be fooled for a minute, of course. Because, for example, there are no dust lanes in any of the galaxies, which is a bit of a giveaway. But there are things you can do which are quite interesting with the simulated one that you can't do with the real one. For example, you can put boxes around all the ones which are actually in the cluster. And that's kind of interesting. So no one's surprised that this one's not in the cluster because the colour's wrong. But this one's not in the cluster. This one is in the cluster, even though it's big. There's more things. And then there are things in the cluster way out here. So the cluster is much bigger in reality than what you can see when you look at this kind of image. So this allows you to assess observation of what you might look at. So this is all available. There are large surveys that have been done recently, like the CFHT Legacy Survey or the Campbell's Cosmos Field, have all been simulated. They're there. You can download it, make these images, do what you like. So far, my impression is that take-up's not been very strong, so maybe this is not really what the viewers want. But we'll see. So if we ask, how do we actually learn something that we want to know from simulations of this kind? So people have a tendency to do these simulations, say, I made this model, and it fits the mass function perfectly. The clustering is great. And look, this is the distribution of colors. This is a factor of 2 orders of magnitude in galaxy mass, and the colors distribution is fairly similar to the observational one. So all this is great. But this is what we put in to calibrate the model. So maybe we learn some parameters and some efficiencies from that. But most of this is there by construction. Where you really learn things is from the things that don't fit. So actually, if you go outside the range I showed, the colours don't fit at all. And that is because the observed galaxies are a lot bluer, the small ones, these faint galaxies are a lot bluer than the ones in the simulation. That's why we had to change environmental effects on small galaxies. As I showed you, the clustering is bad once you've got a smaller objects. This is telling us that the way the galaxies are populated in our outer halos is not correct. And now we can understand by varying parameters why this is, what aspect of this is wrong. I showed you the resolution for this. This is apparently a fact that the small galaxies form too early in the model, the original model here, as a result of the fact that when the material was blown out, it fell back too quickly. So it kept making stars. What seems to happen in the real universe is the stuff gets blown out and then it stays out for a long time. It may eventually come back, but not for a long time. Once you implement that, then things feel a lot better. So, these disagreements, is it due to cosmology, star formation, the way you put the chemical enrichment in? Is it due to environmental effects, maybe it's the clustering? The only way to test this is by taking additional data and then varying what you assume in the model to see how it affects the outcome, because all the different processes are strongly coupled. So I think in this it's really important to remember what we're actually trying to achieve. So I don't think the goal of running the simulation is to fit the observations. The goal of doing the simulation is to learn more about the physics of how galaxies form and whether that might or might not affect cosmology or cosmological measurements made using galaxies. But I think the game is to improve our understanding of the real world by framing some kind of hypothesis about how things may work, and then testing it. So in practice, because we can't follow the physics, once you frame the hypothesis, you then have to calibrate it using some set of data, then you test it by looking at a different set of data, hopefully as different as possible. So to conclude, I think the initial conditions of galaxy formation are precisely known, both in terms of the content, the amounts of baryon, dark matter, and radiation, and the structure. And there are still some issues about the very smallest scales, but over most of the scales that are relevant for galaxy formation, we really know it well enough. Simulations of nonlinear structure growth give precise and quite detailed statistics of the assembly histories of the dark matter for any of all the relevant masses. And then the question is, how do we deal with the baryons? So what I've been advocating here is an approach which gives up on dealing with baryons on the nonlinear scales at all, puts this in a simplified way, and as a result is able to treat very large volumes and large numbers of objects. So the implementation of these simplified treatments of baryon processes has an advantage, as I showed you, that at least the results then become numerically converged. So the results really are a consequence of the simplifying assumptions you made, not of the resolution of your underlying simulation. But they may be not numerically converged and wrong. In fact, they almost always are. I mean, often they're not numerically converged either. They're almost always wrong. So once you have them, then when you understand what is wrong, then you figure out what you need, where you need to improve your understanding. You do this by comparing directly with galaxy abundances, scaling relations, clustering, all of which are found in large observation surveys, and now these are actually measured quite precisely back to redshifts of 3 or even 5 or 6 for some properties. And then these comparisons show how the galaxy formation and the cosmology interact to influence the observables. And so by understanding this, we can characterize both the primary galaxy formation processes themselves, but we can also, by doing that, we can assess the systematics that are likely to be present when we try to get precise cosmological information out of galaxy surveys. Because in the end, we're using the galaxies to measure something about the dark matter or the early universe. We need to understand the connection at a sufficiently accurate level to be sure that we are measuring what we think we're measuring. So I'll stop there. I think most of the abundance information is, at this stage, relatively easy to fit. What's not being looked at nearly as much as the clustering information. So there's a lot more information about the spatial distribution of galaxies, and particularly how that depends on the type of the galaxy and the properties of the galaxy, which is not being looked at in much detail. So this probably is related to how environmental processes affect the galaxies to a large extent. So that's still there to be mind. I think there's still fairly early days also in combining to look at wavelengths away from the optical. So the obvious place to look first would be in the infrared to see all the absorbed starlight re-radiated. And there's some work along those lines, but there's still quite a long way to go. So I'm not sure that there's a major challenge. Again, people tend to publish papers where they fit one thing and say it fits perfectly, and then it's hard to get an overall picture about whether that model still fits everything else. But I think that's, I don't think it's solved, but I don't see a major problem there. There are problems to do with black hole growth and, for example, the growth of the first black holes. I think it's still quite open. That's hard to address with the kind of models that I've been talking about here, I think, because basically we have so little information from those epochs that we don't have much to constrain things with. There's quite a lot of data now also about the circumgalactic medium, so that's the gas surrounding galaxies, which is not heavily contaminated with heavy elements, which are obviously material that was formed in the stars and then blown out. So by looking at this in more detail, you should be able to understand at least the exchange processes between the galaxies and the surrounding intergalactic medium. So that's also at the early stage.
Okay.
That merger tree that you showed, is this driven by purely gravitational dynamic friction? or do you have also a bullet cluster line effect in there?
Well, this is taken directly from the simulation, so it's just gravitational.
I mean, what is the physical mechanism driving that?
Well, a significant fraction is already in the initial conditions. The things fall together because they were initially bound in the initial fluctuations. So a large part of the merger tree is just the larger and larger structures collapsing, and as they collapse, then the pieces they're made of tend to run into each other. So that's part of it, and then once they do run into each other, then the dynamical friction effects and so on are important. Then the bullet cluster is just an issue of whether things run to each other as fast as is observed in this particular case.
Yeah, so, and then the baryonic matter and the dark matter is really separated. So
that's because the baryonic matter shocks and the dark matter doesn't. So.
That is not involved.
Well, no, because I'm only putting in the baryons after the fact, right? The simulation of the end of dark matter.
In star-cluster simulation, they have a lot of problems with small changes in stellar evolution models, like in Higgs, defects, chemistry. So this changes, especially then how the colors, the parameters. Has this been tested here? Or?
Yeah, so I mean, as you might expect, dust modeling is a real mess, and it's something which people don't put much attention to, but of course it makes a huge difference to the observed properties. So this is why having the full spectral energy distribution, so you can get the total luminosity, bolometric luminosity, would be very helpful.
You have made several times the point about the reincorporation of ejected material. Is there really a need for reincorporation? Could you expect that to get into a quasi-steady, at least on the statistical axis, quasi-steady intergalactic medium, which is full of ejected material?
Well, an interesting thing about the Lyman alpha forest is that it's very well fit by a model in which the intergalactic hydrogen is unmatured. So that means that most of the line of sight, sort of quasars of these redshifts, which is then, because they're random 97s, most of the volume has to have been unmatured by bubbles. So the bubbles around the galaxies actually don't fill the volume, at least at redshifts 2 or 3, and probably still don't fill the volume completely even today, although it's hard to tell. So, why do you need to reincorporate it? Well, you can try and make a model where material is not incorporated, and it doesn't work very well. I'm not sure it's far enough away to consider this was excluded.
I wonder about the discriminating power of all this rich data on galactic populations now and in the future. Can you really falsify dark matter on some final level? Or can you always put it in one of these combination of all these baryonic physics parameters?
Yeah, no, you
can
falsify dark matter.
Could have gone wrong, but if you really want, let's say, to compare it by galaxy population with some warm dark matter or something like that.
No, you won't. I don't think you will falsify it by these kinds of observations. But you can falsify it because cold dark matter predicts that there should be structures there with no galaxies. So if you show that the structures do not exist, then you will falsify cold dark matter. And that is possible through certain kinds of lensing observations. So that I think could falsify cold dark matter, but this guy would work well. And I think it's much more strongly affected by the galaxy formation physics than either by the cosmological parameters or the nature of the dark matter.
Okay, final question?
What is the main physical origin of this plateau that you have in the mass function before the fall-off starts at 10 solar masses? You showed when you include the winds, it becomes even more pronounced than the minimum. But what is the origin in the first place?
Well, if you don't put the winds in, you don't get a plateau. So this you need some, because in this particular coordinate system that I'm making the plot here. This one. If you just show the dark matter distribution, it would look like a parabol, drop like this. So what happens is the dark matter will go like this. So this ratio is a suppression due to the feedback effects in the model. So effectively, the scaling of the effects of the winds, the reduction in efficiency has been set in order to produce the observation. This is how we calibrate how it must have worked if it's really a cold dark matter universe.
Okay, so let's thank Sam again.